All right, good evening. We're going to get started here. My name is Greg Fisher, president of Shannon & Wilson, and on behalf of Shannon & Wilson and the University of Washington Civil and Environmental Engineering Department, I want to welcome you to our 2023 Stanley D Wilson Memorial Lecture. It's great to see so many of you here and online streaming. This year we celebrate our 69th anniversary since the founding of our firm by Bill Shannon and Stan Wilson here in Seattle. William Lovejoy Shannon, Bill, was involved in many high-profile projects during his time at Shannon & Wilson. He was also an astute businessman who became the founding president of the Associated Soil and Foundation Engineers, now known as GBA, as well as a founding member of Terra Insurance, a group formed to provide professional liability insurance for the geotechnical engineering community. Bill passed away at the age of 92 in 2006. We appreciate his contributions that he made to our profession. Our other co-founder, Stanley D Wilson, has often been characterized as the idea man, but he was really a tinkerer. As a child, he built his own telescope, including grinding his own glass. He grew up in California as the third of 7 children. He did 2 years at Sacramento Junior College, but had to drop out because of the Depression. He spent 9 years at the California Highway Department, and when World War II started, he was signed to the Corps of Engineers, where he took engineering courses and was sent to Harvard for a 6-week course where he first met Arthur Casagrande. Following the war, he went back to Harvard, where he worked as a TA and RA to Casagrande, and that's where he met Bill in 1947. In 1948, he received a MS degree, even though he never received a BS degree. He stayed on at Harvard as an assistant professor, but he didn't want to get a PhD to continue in a professor role. And thanks to Casagrande, that is where the Shannon Wilson story started in 1954. Stan was technically gifted and was respected for his extensive knowledge of earth and rock-filled dams and instrumentation. At Harvard, Stan built the first slope indicator, which is now known as the inclinometer, at the suggestion of Carl Terzaghi. He developed other instruments to measure displacements and distortions in soil and rock, many of which are still used today. Stan served as a consultant on large projects all over the world. One year, Bill noted that Stan had over 300,000 airline miles. On one of his consulting trips, he contracted malaria, and in 1985, his career was sadly cut short by an untimely death from complications due to the illness at the age of 73. To honor Stan's legacy, our firm established the Wilson Lecture in 1989 to foster and maintain the spirit of thoughtful and practical engineering solutions. For this year's lecture, it is an honor and a privilege to have Dr. Patricia Culligan, who will present on urban water management, climate change, and green infrastructure, a very timely topic. Dr. Patricia Culligan is the Matthew H. McCloskey Dean of Notre Dame's College of Engineering and a professor of civil engineering. Dr. Culligan received her BS from Leeds University, England, and her Master of Philosophy and PhD from Cambridge University in England. She is a fellow of the American Society of Civil Engineers and a chartered engineer and fellow with the UK Institute of Civil Engineers. In 2021, she was awarded the American Society of Civil Engineers H. Bolton Seed Medal for her lifetime achievements in expanding the boundaries of geoenvironmental engineering and sustainability engineering to enhance human health and the environment. Dr. Culligan is internationally recognized for expertise in water resources and environmental engineering. She focuses on sustainable urban infrastructure, social networks, and the application of advanced measurement and sensing technologies to improve water, energy, and environmental management. Much of her current research is exploring how green infrastructure can make cities cleaner, healthier, and more enjoyable places to live. She has also worked to improve understanding of the fundamental mechanisms governing water and contaminant flows in soils and aquifer systems. Her work on building energy explores intersections between residential energy use, human behavior, and policy. She has served as the National Academics Nuclear Radiation Studies Board, as well as on the Board of Governors for the ASCE Geo Institute. She has also chaired the National Academy's Standing Committee on Geological and Geotechnical Engineering. And also, she's the author of 7 books, 7 book chapters, and more than 175 technical articles. Without further delay, please welcome Dr. Culligan.
Well, thank you very much for that kind introduction. And thank you also for the honor of delivering the 2023 Stanley D Wilson Memorial Lecture. I was thrilled when I received the invitation, and I was also more delighted when I heard that the focus was going to be on methods and approaches to addressing practical challenges, given all of the contributions that Stanley Wilson himself made to our area of geotechnical engineering. I did a little research about Stanley myself when I was invited to give the lecture. It's not as extensive as the introduction you received, but I did notice that he studied civil engineering at the University of Minnesota, so he had to weather some very severe winter conditions, which I'm finding myself getting through since I moved to Notre Dame in Indiana in 2022. As noted, he actually earned an MS in engineering at Harvard when he was working with Casagrande, even though he didn't receive a BS, and he became an assistant professor in the Graduate School of Engineering, lecturing in geotechnical engineering. It was to Shannon and Wilson's gain and Harvard's loss that they actually shut down the geotechnical engineering program when Stanley was lecturing there, and seeking alternative career trajectories. He clearly managed to land very well as a founding partner of Shannon and Wilson in 1953. I noticed that he was very influential in developing field equipment for determining soil properties and behavior. And he was known for solving engineering problems by combining this quantitative field observation with theory. And I hope that some of the work that I'm going to be presenting today speaks to that particular approach and does honor to this type of approach, which he was so instrumental in founding. I also noticed that he had a strong interest in water resources. What I'm going to talk to you is about water resources. Stanley himself was more engaged in the upstream end of ensuring that we delivered potable water to populations, and I'm going to be talking about the downstream end of how do we manage some of the consequences of water in our environments when we're dealing with stormwater management, which is something that occurs after we've sometimes made use of the water, or occurs because of the way that we've designed our urban environments. So here's an overview of what I hope to go through during this lecture. I'm going to talk about the urban water management challenge, and I'm going to try and put the challenges we face in this area in the context of climate change challenges that we're also facing. And then I'm going to explain why green infrastructure is being considered as a solution to some of these urban water management challenges. And it's also been considered as a solution to some of the climate challenges we face that are not to do with urban water management. And if I have time, I'll touch on that at the end. And then I'm going to go into some work that myself and collaborators have done over the past decade or more on quantifying the performance of green infrastructure in New York City. Like Stanley Wilson, we relied a lot on field measurements. We had to develop some of our own measurement techniques, but we combined those measurements with theory in order to advance understanding. We've done that on a lot of individual GI components that are part of a bigger system that is being introduced into New York City. So I'm going to move on then from talking about the individual GI components to the system level performance. I'll explain why I think that's important. But in addition to quantifying the performance of GI in New York City from the perspective of stormwater management, we've also been engaged in trying to quantify social benefits and stakeholder preferences. Sorry, my screen has gone off here. So I'm going to talk a little bit about that. I think it's important when we start to think about solutions for urban stormwater management, climate change, or other societal solutions that we have to deal with in engineering, to understand whether those solutions can bring benefits more than the specific area we're trying to impact. Can they bring societal benefits? And do people find them acceptable? And then I've got some closing remarks and some lessons learned. I'm afraid the screen has gone off here, so I'll try not to look back so much. I want to, before I go into my lecture, acknowledge the very many students that have contributed to this work. We've had students ranging from undergraduates to masters to PhD students that have been engaged. a lot of collaborators, some of whom are engineers, many whom are not. I've collaborated with anthropologists and social scientists, geochemists, so those that are experts in climate science, and also some of our sponsors. We've been lucky to get sponsorship from government agencies as well as industry. All right, the urban water management problem. How do we define that? If we look at a pre-development landscape and we look at the hydrological cycle that's associated with the pre-development landscape, there's a cartoon in the bottom of the slide there. 40% of the water that falls on a pre-development landscape is returned to the atmosphere in the form of evapotranspiration. About 50% infiltrates into the subsurface and recharges our shallow and deep groundwater systems, and only about 10% runs off the surface and recharges local water bodies, streams, ponds, etc. If we move to an urban environment, the hydrological water cycle looks very different because it's been severely disrupted by the imperviousness of the urban environment itself and by the lack of vegetation that we find in urban environments compared to pre-development landscapes. So 30% of the water that falls in an urban environment is returned to the atmosphere via evapotranspiration. Only about 15% infiltrates the subsurface due to widespread hardscape, and about 55% turns into runoff. So we suddenly created an urban hydrology problem, which is a waste disposal problem, because we have to figure out in our city what we're going to do with this 50% of rainfall that actually turns into runoff when it falls in our city environments. And so what we've done in developing nations is developed a very complicated underground pipe network system that captures that runoff and tries to deal with it. In many older cities like New York City, it's captured in a single pipe system, which is called a combined sewer system, because that single pipe collects not just the sanitary sewage from the city's buildings, it also collects that stormwater runoff. These pipe systems in older cities like New York were only designed to capture about twice the dry weather flow. The amount of urban runoff that's going into these pipe systems right now, because of the expansion of our urban environments, the increased imperviousness of the urban environments, and also the increased population density, overwhelms the system fairly frequently. And there are little weirs in these single pipe systems that eject a mixture of sanitary sewage and that stormwater runoff into local water bodies when the level in the pipe system exceeds a certain amount. In New York City, 50% of days every month you have a combined sewer overflow event. There are about 500 permitted combined sewer overflow points in New York City, to give you an example of the magnitude of the problem. And that clearly leads to conditions where it's unsafe to interact with the local water bodies, unsafe to swim, unsafe to fish, and there are other health consequences of this combined sewer overflow. If we look at more modern day cities where we have single pipe systems, often that stormwater management, that waste disposal problem that we've caused in our urban environment goes straight into a single pipe that just collects the stormwater and it ejects it straight into local water bodies without treatment. So there are other contamination issues associated with the single pipe system, which are not sanitary sewage overflow, but other contaminants that can be washed off the surface. What also happens during wet weather flow in cities, though, is we get nuisance flooding. And it doesn't take a lot of rainfall in many of our cities to cause the type of flooding that is disruptive to everyday urban life and also can be disruptive to our underground infrastructure. And there's an example on this slide here of what I mean by nuisance flooding. We can still go about our daily business, but it's more difficult than normal. Okay, so what is happening under climate change? This slide shows observed change in daily precipitation intensity across the U.S. for two 30-year periods in time, 1951 to 1980 and 1991 to 2020. And you can see in the graphs below, you've got the change in mean precipitation as well as the change in standard deviation. And if we just look at the top, two bars on that graph. In the northeast, we've seen a sort of a 5% change, increase in mean precipitation, and we've also seen a change in the standard deviation. So we're seeing that we're seeing historically that over years, due to climate change impacts, precipitation patterns are changing in most areas of the country, at least to the eastern side. We're seeing increases in precipitation pattern. But that change in standard deviation is also leading to increases in the intensity of precipitation that we're experiencing. This infographic shows observed changes in very heavy precipitation across the country, and this is looking at the heaviest 1% of all daily events from 1958 to 2012. And over that particular period, if you look at the Northeast, we've seen a 71% increase in the amount of precipitation that's been falling. That's a significant increase. Even on the western seaboard, we're seeing an increase in the intensity of precipitation. And when we see these very intense precipitation events, that's when we get severe flood warning, flood warning happening in our cities. And it's also when we're getting the type of floods that are endangering lives. And I've shown two pictures there of floods that occurred in 2021. The middle one is in New York City, and the lower one is in Seattle. So it's these very heavy, intense precipitation events that are going well beyond nuisance flooding, and they're causing flooding that can lead to significant loss of property and also loss of life. So there's sort of two types of flooding that I want to touch on here: nuisance flooding and this more severe flooding. But in both cases, climate change projections suggest in many areas of our country we're going to see more of this: more rainfall, more nuisance flooding, more intense storm events causing severe flooding. Now, so the rainfall intensity in New York City, this is a graphic that's showing that. Is generally of the order of less than 0.5 inches an hour, 10 millimeters an hour. So at the bottom of the graph, this shows from 1965 to 2020. You can see the majority of data points that are displayed are towards the lower precipitation events. The intense duration frequency projections that are associated with the measurements that I'm going to be presenting suggest that these lower intensity events, we're not talking about more than 50 mil of rain. In fact, we're probably talking about less than 50 millimeter of rain. Three events that are circled at the upper right-hand side of the graph are the severe flooding events that have recently happened in New York City. And they're associated with rainfall intensities that are much higher, 1.5 inches an hour or above. And they're associated with storm sizes that are about 100 millimeters or more, 4 inches of rain or more during a particular storm. So that's another way of looking at what we mean by rainfall intensity. Most rainfall intensity events are quite small. The ones that are very disruptive are larger, but in both cases, climate change impacts suggests that we're going to be seeing increases. All right, so how does urban green infrastructure fit into any of this? So if we think about the flooding and the combined sewer overflow events, or even in the case of single pipe network systems, stormwater runoff being collected in a pipe but picking up a lot of contaminants along the way and being ejected into our local water body. These are all associated with this disruption to the hydrological cycle that's occurred as the result of the way that we've developed our urban environments. So people see vegetation or green infrastructure as a mitigation strategy to these problems, because it might be a way of returning our urban environments to the pre-development condition. And what you see on the top is a rendering that is the result of the Manhattan Project, which sort of imagines what Manhattan might have looked like in pre-development time. And what you see on the bottom is what Manhattan actually looks like. So the idea is that if we can reintroduce vegetation back into our current urban environments, we're going to get closer to a hydrological cycle that doesn't generate all of that runoff, so it doesn't cause the flooding and doesn't cause the contamination of our local water bodies through combined sewer overflow events or other such events associated with the single pipe network system. New York City has been very aggressive at trying to revegetate their urban landscape. Over the past 10 years or so, they've had a green infrastructure program that has introduced over 11,000 separate green infrastructure assets into the city's hardscape at the cost of about $1 billion. They're still making progress there. So their idea, as I've said here, is to restore the pre-development hydrological regime of the developed watershed through the design and intervention of green infrastructure. And you can see on the map of New York City to the right, all of those dots represent the assets that New York City's already inserted into the city hardscape. They were inserted in areas that the city identified as priority sewer sheds due to the contamination that was being caused by the combined sewer overflows in the city. But they also identified some priority watersheds based on social justice issues. Might come back to that in the end, because they were neighborhoods that have suffered severe environmental degradation and environmental insults in the past, and they wanted to ensure that these neighborhoods might be the first to receive the green infrastructure, which was trying to ameliorate some of the negative environmental consequences of urban stormwater. However, the cities more recently, and many cities around the world, have started to pivot towards green infrastructure as a solution to dealing with issues like the combined sewer overflow, to dealing with climate change. And we've seen a lot of cities around the world, in the US, in Europe, in Australasia, that have adapted green infrastructure for climate resiliency. I mean, stormwater management is one problem that they're trying to deal with because of the increased occurrence of pollution by stormwater runoff, because of the increased rainfall depths, but also the increased flooding due to the increased storm intensity. So the stormwater management is on the issue, but urban heat island mitigation is also something that people are looking for green infrastructure to help address. The possibility of lowering building energy demands if you put green roofs on buildings, reducing water energy costs, because if you're capturing water where it falls, you don't have to pump it to a treatment plant, so there's energy savings in that, for example. If you capture it and reuse it, there's energy savings in that. And people are also looking at green infrastructure for coastal resiliency. The type of green infrastructure interventions that I'm going to be talking about in the next few slides are not appropriate for coastal resiliency. We're really talking about extensive, wetland areas if we're looking at that, and that's not the focus of the research that myself and my collaborators have been doing in this area. These are the example green infrastructure strategies that New York City has been moving forward with. On the left, you've got green roofs and green streets. They actually capture the storm water or the rainfall that falls upon them, so their watershed is the vegetated area itself. In the middle, you have canopy and vine strategies. These have much more complicated mechanisms for capturing stormwater through interception and stem flow, and then moving the stem flow to a soil system of some sort. So there are multiple mechanisms they use. But the urban street trees are becoming a very popular intervention in New York City for mitigating urban heat island. And on the right, you've got right-of-way bioswales, which are now known as rain gardens in New York City, which are green infrastructure interventions that are put into the right-of-way because the city owns the right-of-way, and it's very easy for them to move forward these type of interventions. And most of the assets that New York City has put into the city hardscape are these type of assets, the right-of-way bioswales. They funnel water from upstream catchment areas that are significantly larger than their vegetated area, 100 or so times larger, so they're very efficient green infrastructure interventions. If you're interested in any of the research that my group and collaborators have done on these different strategies, and we've looked at all of them, you can find a lot of our papers on my Google Scholar page. And I'm happy to answer questions about any of the work we've done here. But what I want to focus on for this lecture are the green roofs. So I'm going to talk about how we quantified green infrastructure performance for one specific type of green infrastructure, which is a green roof. There are two types of green roofs that you can put on urban buildings. One type is an intensive type. They tend to be very deep substrates with vegetation on top of them. Generally, buildings have to be designed to take the load of these intensive green roof types. So we've been studying extensive green roof types in New York City. Extensive green roof types are very thin substrates. They generally cannot support a wide palette of vegetation. In fact, sedums, which are desert succulents, are generally the vegetation that are associated with these green roof types. But because they're lightweight, they can be retrofitted onto existing urban building stock. And given that most of the building stock in developed cities like New York is old, these are the solutions if you want to move forward with widespread implementation of this type of green infrastructure component in an urban environment like New York City. What you're seeing on the right-hand side actually is a residential building at Columbia University, which has a green roof on top of it. Columbia retrofit quite a few of the urban campus buildings with these extensive green roof types. If we look at a cross-section through an extensive green roof, you can see at the bottom there's multiple drainage retention layers that go on top of the roof membrane itself. These type of layers are typically designed by geotechnical and geoenvironmental engineers. And then above that, there's a growing medium, which is actually an engineered soil that has to be lightweight, so it doesn't have the same saturated density as a natural soil. It tends to have organic material and something like a polystyrene or expanded shale to reduce the density of that soil. And then you have the vegetated layer itself. In the case of the green roofs that I'm going to talk about briefly, the vegetated layer is sedum. This particular roof cross-section is probably no more than an inch deep, 25 mil, quite a thin retrofit. There are three types of extensive green roofs, and we've studied them all in a network of green roofs that we set up around New York City that's been operating for more than a decade right now. There are the complete green roof systems. A complete green roof system, you take all of those components, those different layers, up onto the roof, and you construct the green roof on the roof yourself. It's the most expensive system mainly because of the labor involved. You literally have to get all the materials up there, and it's a construction project to get this done. The second type is a modular tray system, so you put all the layers in a tray, and then you take the trays up to the roof, and you sort of lay them out in a pattern, as is shown in the middle photograph here, to construct your green roof. These are the second most expensive type of system to construct, unless you have free labor. A lot of the schools in New York City have these type of systems because they have the students construct the layers in the trays and bring them up to the roof as part of a sort of an educational and learning experience. The bottom is a pre-cultivated vegetated mat. You've got to think of the layers being assembled off-site, even outside the city, in something that looks like a carpet, and the carpet gets rolled out onto the roof. This is the cheapest. It tends to be the most lightweight. This is the system that Columbia University chose when they decided to retrofit some of their buildings with green roofs. Each of these systems behaves quite differently, and that's some of the work that we've been doing to understand the behavior. This is a typical hydrograph. On the left is a cartoon of a hydrograph for a green roof. You have a volume of water that enters the roof through precipitation, and then the runoff from the roof is reduced by volume, and the peak intensity is reduced, which is why we're helping combat the combined sewer overflow system with this and reduce flooding. And the right are some data that we've measured, with the blue being the rain hydrograph. Rain hydrographs are not as smooth as the cartoon. The rain is very peaky. You get periods of high intensity and low intensity, and then the green is the runoff from the green roof. And then the black line is what would happen if you didn't have a vegetated roof. Non-vegetated roofs do also capture stormwater, just not to the extent that a vegetated roof will. We studied about 7 green roofs across New York City. We instrumented them. We collect data remotely, so there are data loggers on the roof that are throwing the data that we collect up to the cloud. I'm going to quickly present data from 3 roofs. One, A is a pre-cultivated mat, the thing that you roll out as a carpet. B is the tray system, and C is a roof that was constructed in place on top of the USPS, United States Post Office system, Morgan facility, downtown New York. Roof A was located at West 118th Street, so we called it West 118th roof. Roof B was located on the Con Edison Learning Facility, so we called it Con Ed. And because C was located on the USPS postal facility, we called it USPS. You can see that we lack imagination. But it also helped us keep track of where the roofs were when we were discussing them. So our field measurements, we needed to measure the precipitation. That's fairly straightforward. Didn't have to do any new instrument design for that. We just put weather stations on the roof. We also had opportunities to measure wind speed, relative humidity, and temperature, so that we could look at estimates of evapotranspiration. We put moisture content sensors in the substrate of the green roof that also helped us figure out the water balance for the green roof, including the evapotranspiration. Where we did have to develop new instrumentation was to measure the runoff. So we developed weir systems that were configured specifically for the roof type. And what you see at the bottom is a weir system that was configured for a roof where the runoff goes outside the parapet and then down an exterior pipe on the outside of the building. This is sort of typical for how drainage happens on older buildings in New York City. Newer buildings, there are watersheds on the roof and the pipe is interior. So you have to measure the water flow into the pipe because it collects all sorts of other water on the way down the building and into the sewer system. So our weir systems used level measurements. We found V-notch weirs were the best to use. As I said, we customized them for each of the configurations that we had. So this is sort of some of the instrument design that we got involved in when we were trying to quantify how much stormwater these green roofs could actually capture. With the runoff measurement, and we collected the surface flow as well as the base flow, the precipitation and the measurements from the soil moisture probes, we could do a full water balance on the green roof. I'm just going to really present the runoff or the retention because that's the focus of this particular talk, but we actually have a lot more information than I have time to present. So these are some examples from the roof that was on West 118, the Columbia University roof. That's the vegetated mat system, the one that you roll out like a carpet. On the top left-hand side, you have the runoff from the roof versus the atmospheric precipitation on a log scale. The solid black line would be if the runoff was equal to the precipitation. So the roof wasn't really doing its job. It wasn't capturing any stormwater. And you can see all of the data points generally lie underneath the black line, with the exception of a few. But the higher the precipitation, the closer the data points get to the black line. That makes sense. The roof is capturing less stormwater as less rainwater as the rain depth increases. You'll also see that we looked at the residuals. We fitted a model, an empirical curve through our observed runoff data that we call a characteristic runoff equation for the roof. We developed these for all of our roofs. Not surprising, the empirical-based model that was derived from field observations is the best predictor, but I think that's somewhat circular. But we looked at the residuals from our empirical model, which you have on the bottom graph, versus observations, and you can see a clear seasonal pattern here. So the empirical model underestimates the runoff in the sort of the winter months and the shoulder seasons, and sort of overestimates the runoff during the summer. And that's because during the summer you're going to have much more evapotranspiration because the vegetation is healthy. You have a lot of biomass. You know, it's also hotter, et cetera, et cetera. So we've developed more sophisticated models, and which actually take into account seasonality. So we've got models that are a function of rain and Julian day. Julian day is our surrogate for seasonality. We can actually replace that with seasonal parameters, but this is the simplest form of the model that I'm showing here. But we also have antecedent dry weather period in the model, because even in the same season, if you get one rain event that's large, back to back with another rain event that's large, the roof is going to lose its retention capacity. So the dry weather period makes a difference to the ability of a roof to retain stormwater. But we found with adding the Julian day and the dry weather period, we can predict the performance of these roofs with our empirical approach with quite a great deal of accuracy. Okay, so what does that mean? When I go back to the role of the green roofs, not only in retaining stormwater, but also in thinking about them as a sort of an intervention for dealing with flooding. So what we have here are a comparison against the different green roof types that I mentioned earlier. So on the left we have the Vegetated Math system. I just showed you some more detail about the measurements and results from that system. In the middle we have the Con Edison tray system. Expensive unless you get school children to construct the trays for you. And then you have USPS, which is the complete system, which is very, very expensive. These are box plots that show the retention behavior of those three roof types based on our empirical models and 50 years of precipitation data that we got from the New York City Central Park weather station. So you can take the empirical models and you can run them through every storm that New York City has seen or logged, and take into account the Julian day and the antecedent dry weather period. So if you look at storm events that are less than 10 millimeters, or all of the roofs are sort of retaining 65% or more of those storm events. Most of the combined sewer overflow that happens in New York City, most of the events, the N of the events, happens for storms that are 10 millimeters or less. So they could do a lot if you could cover a lot of the rooftop in New York City with green roofs. They could do a lot when it comes to attenuating the combined sewer overflow pollution problem that New York City has. If you go to storm sizes that are intermediate, 10 to 20 mil, they're still sort of doing above 60%. So even if we see a changing shift in precipitation that is increasing storm size, with climate change, we're probably still not going to move much from the 10 mil to, maybe 12, 13. So I think for the combined sewer, we're sort of okay. If you get to the larger storm events, they do worse. And then when you get to the storm events that are 40 mil or more, we're below 40%. The reason we stuck with the 40 mil or below is we don't have enough observations to do a decent modeling or statistical analysis for anything that's above 40 mil. If you look at the nuisance flooding, which is sort of where the intensity is about 0.5 inch or below, most of the nuisance flooding is happening in these storm ranges. So the green roofs are going to have an influence on reducing nuisance flooding. Most of the extreme flooding is happening well outside of this range. And if you see when you're at 40 mil, you're only getting 30% retention or more. You can imagine if you go to 100 mil that they're not going to be retaining very much. I think we only have one or two storms where we actually were able to capture that amount of rainfall. what happened in New York City when the extreme storms were moving in is everybody that owned a roof which we were instrumenting, and they were all private roofs, said, could you please get your equipment down? We've got a hurricane coming in, so that was another reason why we weren't able to capture the behavior. But I think these type of interventions are probably not going to be that effective for dealing with the flood events where we're talking about potential loss of life. They're probably going to be quite effective, quite to moderately effective at the nuisance flooding. And they're doing a reasonable job at keeping stormwater out of the sewer system. We did some measurements combined with modeling. You can actually do a bucket model if you know the precipitation that falls on a green roof and you have the soil moisture measurement. It's quite a simple water balance to predict the runoff from those two parameters. And we sort of liked this because it reduced the amount of instrumentation that you had to put on the roof. We didn't need to measure the runoff, assuming that we could get a good prediction for this. So this is where we're sort of combining physics with instrumentation to come to some conclusions about a system behavior. So here are some example outputs that we got from this simple bucket model, which we called SWAM. We're comparing the runoff that we predicted with SWAM on the vertical axis. If you look to the left-hand side of these plots with the weir runoff, and they're actually a very, very good, decent correlation. So just with the soil moisture measurement and rainfall, we can actually predict green roof runoff pretty well. We're also looking at predicting evapotranspiration here, and it wasn't so bad either. But what you see on the right-hand side is what I was trying to explain with the rainfall depth and the rain intensity. Most of our rainfall depths were below 50 mil, and our intensities were about 10 mil an hour, sort of half an inch an hour, so falling within the standard range that we see for New York City. But when we get to rainfall depths and intensities that are sort of more like the flooding events, we don't have very many data points, and these type of simple bucket models don't work. And that's probably because they don't account for things like depression storage, and they don't account for ponding on the surface and things like that. But we can do a decent job with just a soil moisture reading and just a rainfall gauge reading. We found that with a lot of the different green infrastructure types. We also did process-based approaches. I'm not really going into this, but we wanted to see, well, if we didn't have any measurements on the roof, could we sit in front of our computers with a model and predict what was happening? And you can to some extent, but the process-based models tend to underestimate the peak runoff, which is a problem if you're trying to figure out how peak runoff might support or not a reduction in combined sewer overflow events or flooding. So they tended to do that for the small storms, and then they did an over-prediction for the larger storms. So they were good, but we're still a long way from being able to just use a model to predict the behavior of these complicated infrastructure systems. All right, so I'm going to just summarize what we found from quantifying green infrastructure, just from a stormwater performance point of view, and I'm going to come back to the flooding at the end. So we think for most green infrastructure systems, a simple soil moisture measurement combined with some physical model. For the green roofs, it's straightforward because you can use a bucket model because their watershed is their vegetated size. It becomes more complicated for other systems. But if you combine soil moisture with a simple physical model, you can quantify green infrastructure performance pretty well. So that means that we can move to quantification systems that reduce the instrumentation that we need in the field. A lot of the research that myself and my collaborators have been involved in is pretty intense field instrumentation and field observation work. But I think we have enough data to demonstrate that we can move to a different phase. And these simple models are more accurate than any process-based model right now. So you could maybe imagine a world where you have a lot of green infrastructure interventions with soil moisture measurements in them. You're collecting the soil moisture measurements in a cloud system. You've got your Met system, and you've sort of moved into sort of a big data scenario where you've got a lot of data that you can combine, and you can start to predict system performance using potentially machine learning methods. And that's where we've gone with some of this work. But even if you don't want to do system level performance, you could probably understand the performance of each individual GI component. All right, so now I want to move on to some explorations we've done with system level performance. So our group and many others in the US and around the world, I think have gathered an enormous amount of data on how individual GI components perform. What do green roofs do? What do bioswales do? What do tree pits do? But the point of the green infrastructure program in cities like New York, and the point of programs that have been proposed in other cities, are to put in thousands of components that somehow act as a system and try to ameliorate the problems that we want to address. So, New York City is not necessarily interested in what does every individual green infrastructure component do. They're interested in stopping combined sewer overflow pollution, and they're now interested in stormwater management holistically, thinking about nuisance flooding, urban heat island. So we're sort of talking about how do thousands of components feed into a larger goal, as opposed to how does each component do something. So to try and explore systems level components, we started to look at the issue of whether green infrastructure actually reduces water pollution, because that was the first reason that New York City introduced its aggressive green infrastructure program. So to do that, we needed to have an understanding of the water quality problems around the city. So we collected enterococci samples at 50 sites across New York City for a period of 7 years. We used citizen scientists to do this. And we built up a fairly large database, and we were using the enterococci concentration as an indicator of fecal contamination. So this was us saying, what does fecal contamination look like at these different sampling points around the city, over a period of multiple years. So that was one data set that we used to answer this question. This is a series of box plots collected at the 50 sampling sites, which are sort of on the horizontal axis. I left the name of the sites out to avoid crowding of this graph. The vertical axis is the enterococci concentration, and the red dashed line is the line that the EPA sets for ENT concentration for swimmability. If your ENT concentration is below the line, the water's swimmable. If it's above the line, the water's not swimmable. So these red box plots are concentrations when there was no rainfall. So you can see it at some of our sampling sites. You can't swim in the water even if there's no rainfall. So the combined sewer is not making any difference. You shouldn't get in the water at that particular sampling site. The blue bars are what's happened 6 hours after we've had a rainfall event. And so you can see that 6 hours after a rainfall event, at most of these sites, the concentration goes up because the combined sewer overflow has started to pollute the water. In the cases where you can't even swim anyway, maybe that's a concern, maybe that's not. There are cases to the far right, though, even after a combined sewer event, it looks like it's swimmable. So we've got these two interesting extremes. Even without rainfall, you can't swim. Even with rainfall that increases bacterial concentration in the water, you still can swim. So how does green infrastructure fit into any of this? In order to have a surrogate for the green infrastructure interventions that have been put into the city hardscape, as well as the green spaces that already exist, because they're soaking up rainfall, even though they weren't part of the green infrastructure program. We use the runoff coefficient as a surrogate. And we actually have a map of the city land use at about a third of a meter by a third of a meter resolution that we developed with some colleagues over multiple years. And we can use the city land use to get a runoff coefficient. For the green infrastructure interventions, we already knew the runoff coefficient because we'd been modeling them and we developed our empirical relationships. So where we actually had the information, we used it. Where we didn't have the information, we did a literature survey. But you'll see that there are 9 major land use cover conditions in New York City, and each of them has an associated runoff coefficient. So we created a map of runoff coefficient for New York City with the idea that if the runoff coefficient, which is the fraction of the runoff caused by a rainfall event. So a high runoff coefficient means most of the rain turns into stormwater runoff. A low runoff coefficient means most of the rain is captured. So you've got these two extremes. We represented green as a low runoff coefficient. So the runoff coefficient is a surrogate for how much rainwater gets soaked up, which is then sort of a surrogate for the amount of greening in the city. All right, so that's another data set that we put in. We did a cluster analysis of runoff coefficient versus that ENT concentration. And we found in some cases, there was no correlation between runoff coefficient and the amount of contamination that we were seeing in the water. And you can see the green dots, they're the green dots where we're seeing no relationship. It's sort of all around the outside of Manhattan and on some of the sort of water bodies in Brooklyn. And then there are red dots where we see a relationship between concentration and runoff coefficient, so the pollution in the water and the runoff coefficient. When there's high runoff coefficient, a lot of stormwater running off, pollution's worse when there's low runoff coefficient. So in order to understand what was going on, we ran a supervised machine learning algorithm, which is a random forest model, to try and predict conditions when you could swim and when you couldn't swim in the waters. So we're trying to say, okay, what leads to waters being swimmable or non-swimmable based on the measurements that we took? Turns out that the biggest predictor is flow speed. So 6 hours after a rainfall event, combined sewer goes into the local water body, but if the local water body is fast moving, it cleans up quickly and you can swim. The second things were the sort of the area of the sewer shed associated with the combined overflow, because if the area is bigger, you'll pick up more stormwater and that will overwhelm the system more. The third thing was the amount of rain, which makes sense, and then the runoff coefficient, which is our green infrastructure surrogate, was fourth. So I'm presenting these data because how and why we insert green infrastructure into our cities to combat climate change, to combat combined sewer overflow events, to combat the urban heat island, really depends on what we're trying to achieve. If we're trying to achieve clean waters, we shouldn't be putting green infrastructure in areas where the water body is rapidly moving, because it's really not going to make any difference. If we have very small sewer sheds, that's probably also not going to make any difference. But if we have slow-moving water bodies and large drainage areas, green infrastructure is going to make a difference. So this is the type of connection between the individual component behavior and the system-level response that I think we need to move forward if we're going to do sensible designs of green infrastructure programs. And by green infrastructure programs, I mean the collection of the individual components. It doesn't mean that we shouldn't be doing sensible designs of the individual components, because their collective behavior is going to feed into something like this. But we also need to keep an eye on how does the system behave overall. So if we go back to the flooding, we need to do this for the flooding too, where we're sort of hamstrung right now, because our data set, instead of the water pollution data, the ENT concentration needs to be the depth of flooding around the city. We're sort of hamstrung because we don't actually have that data set. But we're collaborating with somebody in Stevens who is gathering that data set. And with that data set, we can do something similar, saying what is leading to local nuisance flooding, what are the main causes of that, and can greening influence that? So that's sort of where we're moving with the flooding. But we started to develop a methodology to try and answer these systems level questions. We've been doing this for the urban heat island too, a similar approach, and we've actually found that you can reduce surface temperatures in an area if you have a certain configuration and pattern of green infrastructure. So that sort of also goes beyond a little bit the individual component. It's how you organize the components in a pattern that will make a difference. So I just want to move to quantifying the social benefits before I finish. So this is a lady in Queens. A bioswale came her way and she was not very happy. We found this working in the field. A lot of our field work in bioswale measurements was actually in the environmental justice areas that have been targeted for green infrastructure. We went into those neighborhoods, and the folks in those neighborhoods were unhappy about this too. They were unhappy because they were living in public housing where the boiler was broken. They said, why is the city putting money into making the place look beautiful when, I don't have any heat? They were concerned about gentrification, pushing the prices up in their neighborhoods. In any neighborhood, people think these things, they take away parking. That's a big deal in New York City. Somebody takes your parking spot away. They don't actually take parking away, but you really wouldn't want to open your car door into this. So in general, we our own work, just interacting with the public when we were doing our measurements, indicated that there wasn't a lot of public acceptance for these programs. So we started to dive deeper into understanding why that was the case. And we started to try and quantify how people value green infrastructure and why they value green infrastructure. We did multiple stakeholder surveys using an ecosystem services framework that the United Nations developed. And we found that from the stormwater perspective, people really just valued the green infrastructure that was vegetated, although there are many other ways that we could think of green infrastructure, like rain barrels that would capture stormwater that is not vegetated. But we found that the vegetated land people valued most. But when we sort of looked at why people valued green space in their environments, it was actually for the cultural and social services more than the environmental services. So people weren't saying this is great, you're ameliorating stormwater runoff problems, I think nuisance flooding is decreasing. They valued the way that greenery in the urban environments allowed them to interact socially, and they valued the cultural benefits. And I think that's something that we need to take into account as we move further forward with these green infrastructure programs, which, as I said, are going beyond stormwater management. They're going into climate adaptation and resilience right now. We also looked at relationships between urban greening and reported subjective well-being, and we found that there are certain types of greening that people value. The sight of trees makes people feel happier than maybe the smell of grass. So there is also a certain type of greening. So people are valuing greening for social and cultural reasons. They're very specific types of greening. We also found that there's a size component associated with this. Like a small bioswale is not the same as a pocket park, where you could sit on a bench, interact with other people. It may have the same stormwater, the pocket park and the bioswale may have the same stormwater benefits per area, but they have very different social benefits. And we finally did some work during the pandemic trying to understand the relationship between access to green space in a time that was, very stressful and isolating for a lot of people. And we did these survey results during lockdown. And we definitely found that access to green space increased people's social well-being or reported social well-being during the pandemic. So I think these are all components that we need to think about in our urban green infrastructure planning. Finally, we started to look, and these results are a little worrying to me. We started to look at different stakeholder preferences for urban stormwater water management, both now and in the face of climate change. We looked at the plans from multiple cities across the world, a couple in North America, a couple in Europe, and a couple in Australasia. These were all developed cities. And if we look at all of the stakeholder participants, and the stakeholder participants were community groups, they were policymakers, they were engineers, they were people in charge of maintaining green infrastructure. And the preference for stormwater management, the intervention preference is green infrastructure. You look at the bottom of this table, what is ranked at the bottom is gray infrastructure. So we're sort of also seeing a policy landscape and a stakeholder preference that's moving towards vegetation as being the solution to our stormwater management issues now and in the face of climate change. And why I think this is concerning is that the probability of us being able to deal with the flooding events that are beyond nuisance flooding events with green infrastructure alone is low. Like, we're going to have solutions that combine green infrastructure and grey infrastructure. And they're going to have to take into account that we're seeing these changing precipitation patterns, more intense events. But if we don't combine the grey and the green infrastructure, if we just move down this pathway of thinking that the green infrastructure systems are going to be able to deal with everything, including extremes, I think it's going to be hugely problematic. So this is just a snapshot of where current policy and stakeholder preferences are moving, definitely towards more vegetation, but I think at the cost of really understanding the challenges that we face in dealing at least with some of the extreme events. This is my final remarks, my lessons learned. So we have a pretty good understanding of the performance, either via observations and this physical modeling of individual GI installations and types. So I think there's a lot of work being done in this area, and it's resulted in some good outcomes. So we can say what each individual GI type does when it comes to retaining stormwater. We've got a lower level of understanding of how GI performs as a system of tens of thousands of components. We've started to try and put in place a framework for linking between these two different scales. And we've made the progress for water quality and really identifying what is impacting water quality, so we can hone in on where green infrastructure interventions are useful and where they're probably not going to make a difference if swimmability is the outcome we're looking for. I mentioned that we started to make progress on urban heat island, but we do need to make more progress on the flooding during wet weather flow, and that's going to require measurements that we currently don't have. Just as a sidebar, we've tried to use the 311 database in New York, where people report flooding, and it actually turns out to not be accurate enough to really answer the question that we need to answer when it comes to the role of green infrastructure in reducing flooding now and into the future with the changing rainfall patterns. I do think we're going to need a mixture of grey and green infrastructure, and it is a little concerning that we're seeing people devaluing grey infrastructure as part of the solution here. We have to think about social values and social acceptance of these systems. As engineers, I think we have indications from some of the initial work that we've done, but more needs to be done. But I think if we design these systems to maximize social benefit, then that's a better outcome than just designing them to achieve the engineering goals that we're moving towards. And we managed this by advancing field measurements and combining them with theory and modeling to support decision-making in urban stormwater management, but I want to go back to the fact that Stanley Wilson was doing this decades ago, so he really was a pioneer and leader in this field, and we continue to use the methods that he established to try and build engineering systems that benefit as many people as possible and tackle some of the challenging problems we face as a society today. So, thank you.
My name is Bob Mitchell, and I'm the chair of the Shannon Wilson Board of Directors. I believe we have time for a few questions, either online or certainly from the audience. Back there, I can barely see you in the light.
Sorry. I was curious, you mentioned having to remove your equipment during like the hurricanes, the significant rain events. Did you see any issues with like soil degradation or losing some of that vegetation on the rooftops during those events that would require like additional maintenance to maintain those roofs?
So just to repeat the question, was there degradation or losing of materials during some of the larger storm events for the people online?
Yeah, we did not see any detrimental effects to the green roof systems or the other systems we were monitoring, but the erosion of the substrate can be a challenge, and we found it's a challenge on the sloped roofs. And so some of the substrate is quite fine, and over time with the sloped roofs, also some of the flow in the substrate is going to be down the slope. It was just constantly washing the fines out, and we'd find them in the gutter system at the end, and they were definitely reducing their capacity. So I would say it's more the configuration of the roof that was leading to erosion. We didn't see anything during the larger events.
Can I ask a follow-up question on that one? If you're seeing like soil erosion, like plants require specific nutrients and stuff, did that factor into any of the pollution monitoring that you were doing?
The only pollution monitoring we were doing was that fecal indicator. We actually have done nutrient balances on most of the green infrastructures. They actually all export nutrients, but we didn't link any of that to soil erosion. So unfortunately, I don't have any insight into that.
Others? Yes.
Can you compare the use of green infrastructure and compare that in an urban environment to like London, where they've used a massive system of tunnels for combined sewer overflow to clean and address the flooding issues?
So the question is about comparing combined sewer overflow to someplace in London and other major cities.
Yeah, so different cities have different approaches to this, and for example, in Singapore, they've actually built underground tunnels to deal with this, or they've actually have tunnels which are normally passageways for cars that during a big storm event they will close and turn them into detention basins. I think there are other cities in the world where they've used the underground pipe network itself as storage, because the sewer system is not equally overwhelmed everywhere. So if you could pump the water around underground in the sewage system, which is sort of maybe some of the solution that they have in London, it wasn't available in New York. So I think it's really difficult to compare and contrast unless you've got very similar conditions and somebody's taken route 1A and somebody's taken route B. The nervousness about building large underground retention systems in New York, and they have done a few, is the cost of construction. I mean, the cost of constructing anything in New York is like pretty prohibitive, but you know, the cost of construction and the disruption that it causes, basically. So the city thought that the green infrastructure was going to be cheaper and less disruptive. That may or may not be true. We had a discussion at lunchtime about the cost of maintaining these systems, and when they first went in this direction, I think they underestimated the cost of maintaining 11,000 bioswales, for example. But I think the other reason that cities have a preference for green infrastructure, as I showed in that table towards the end, is the co-benefits. You know, the feeling that, you know, there are human health and well-being benefits to having a vegetated living environment, that there's urban heat island benefits, you know, that maybe if you have a green roof, it, you know, cools the building and reduces. So I think that's another reason, you know, why cities like New York skewed this way.
Others? Greg. I have a two-part question, and I'll kind of piggyback on what you just said. So the first part is, like in New York City, is the city paying for these private building roofs to get green rooftops, and how does that system work?
Yeah, so the city has two mechanisms, to the best of my knowledge, that they're using. One is a tax incentive program. So you can get tax credits or a tax rebate if you put a green roof on your property. They're very specific about the type of not the type of green roof, but they say it has to be a certain depth. And it's actually deeper than the roofs that Columbia University put on. So you have to have a certain structural capacity, and you have to cover, I want to say 75% of the roof, which isn't possible in most cases due to fire restrictions and equipment on the building. You know, so by constraining the type of green roof that you could put on, I think they reduced the number of people that would go after that as a way. But I also think the incentives and credits are really still not enough to cover the cost. So if you're looking at replacing a roof, you know, the cost of doing a membrane and a green roof versus just the membrane, that additional cost is not covered by the incentive. The second instrument that they've tried is for institutions, like universities, where I think they will support much more of the cost, but you have to put a deed restriction on your building. So I don't think there's any institute, even if it's 100 years old, that is going to accept a 25-year deed restriction on a building just to put a green roof up. So Columbia didn't take any of these. They just did it. So they are struggling to figure out the instrument that would get more private owners to put green roofs on. Philadelphia, I think, started to make progress here because another hurdle is the paperwork to get one green roof on your property is just incredible. So Philadelphia started to move towards a system where there would be middle people that would say, how about I get you 100 green roofs to the city? And then they go to the 100 building owners saying, how about I do all the paperwork for you and just get you the credits? And that, as a system, seems to be a better way of moving forward. So like a middle person that's trying to join the two pieces together.
And the second part I had was, in New York City or any other cities you know of, has there been actual measurements that's shown that we are seeing a reduction from either the roofs or just the whole systems combined, or is it just still all the modeling at this point that's indicating it's going to happen?
Yeah, that's a great question. New York City does the measurements. They're not publicly available. There's a lot that's not publicly available after 9/11 in New York City. Which is why, many of us in this area started to figure out our own measurements and try to build our own models. New York City also has a pretty extensive and sophisticated model because they know where the sewer network is and we don't. So they're combining measurements and very sophisticated modeling. I still don't think 10 years later, though, that they've made the progress that they needed to make at this stage to meet their goals. But yeah, it's sort of behind a firewall in New York City.
Others? Amy?
You mentioned being concerned about sort of the gray infrastructure falling kind of out of favor. Are you seeing that reflected like nationwide or in some states in the actual regulations and stormwater management manuals, or is that more just like a fear based on how people are talking about the subject?
So the question was about gray infrastructure falling out of favor in other states and cities.
Yeah, so those data that I presented came from a study which started with a PhD student who was a visiting PhD student in my group, and he came from a political science background. He studied the climate resilience and adaptation plans of multiple cities in North America, Europe, and in Australia. And he started to pull out, sort of the green versus the gray in those plans. And then he picked 6 cities where he was seeing more of the green infrastructure being emphasized and did a survey of stakeholders. He identified policymakers, he identified implementers, he identified community groups, and he sent out a survey to those stakeholders, and then he did a topsis analysis, and don't ask me what that is because I'm very unfamiliar, but it's a tool that's been used to try and understand how to deal with disparate stakeholders and sort of disparate perspectives on things, and he came up with a table based on that. So that is based on surveying stakeholders in these cities that have climate adaptation and resilience plans that involve green infrastructure. And he was just focusing on the climate adaptation resilience that spoke to the fact that we're going to see more challenging stormwater management issues in these cities going forward due to climate change. So that's where it comes from.
Others? Anything on that? Okay. Well, thank you very much. Tonight's presentation was actually the 30th Wilson Lecture, with the first given by Ralph Peck in May 1989. Our goal of each one of these lectures is to honor and celebrate the legacy and continue the legacy of Stan Wilson. Tonight, I believe we certainly succeeded in that area. On behalf of Shannon Wilson, our staff, our clients, and our colleagues here in attendance, I want to thank you for this excellent presentation and certainly a very interesting topic, as well as your extensive, significant contribution to the profession. Thank you. And then Dr. Culligan, in appreciation of this presentation, I want to give you this plaque and honorarium, and it says, in grateful appreciation to Dr. Patricia Culligan for the 2023 Stanley D Wilson Memorial Lecture, Urban Water Management, Climate Change, and Green Infrastructure. Thank you very much.
Oh, thank you.
So with that, I want to thank all for the Shannon Wilson people for all the planning efforts that went into this. It's certainly extensive, and the coordination, and also our partners here at the University of Washington. Thank you for that. And hope there are some appetizers up on the second floor. I believe you have to go out through the front in room 225, the Walker Ames room after that. And thank you again for coming tonight, and have a great evening. Thank you. Thank you very much.
I don't know what happened to this?
Time out, I don't